Okay, this comes under the title of connected bodies, but you can't treat them as one connected body because they're not moving in the same direction. So we have to treat these as separate entities anyway. Okay, so we're going to label the diagram first of all. We've got tension. It's told us here that this is an inextensible string, and we're asked that later on about it being a light string here, but we're going to actually have tension, so it's going to have tension there, and because it's the same continuous string, you're going to have the same tension in it all the way through, so it's going to be there as well. Two particles A and B of mass little m and 2m respectively are attached to the ends of a light and extensible string. The particle A lies on rough table. Okay, so it's going to want to go across and down, so we're going to put friction on in that direction to oppose motion. The string passes over a smooth pulley fixed to the edge of the table. The particle B hangs freely below the pulley, as shown in the diagram. The coefficient of friction between that A and the table is mu, so we've got mu over here. The particles released from rest with a string taut. Immediately after release, the magnitude of the acceleration of A and B is 4/9 g. So it's going to want to go downwards, not freely under gravity. So that's not gravity, the acceleration, because it's attached to tension slowing it down. So it's going to be less than gravity. As you can clearly see, it is 4g/9. It's a double arrow, and there's a double arrow of this one here also at 4g/9. Now, because it's a rough table, we are going to need to know the resultant force, because the connection between the two is F max is achieved once you have reached maximum and it is moving over the table. That is equal to mu r. So there is a relationship there. Okay, we've got the weight of the mass, which is m times gravity, mg, and you've got the weight of the particle B, which is 2mg. Okay, right. It says find the tension of the string immediately after the particles begin to move. So you've got 3. The best thing to do for that is you've got too many unknowns going on in here, especially with F max going this way. It is to look at this particle. Ooh, edit, undo. Okay, so look at that particle alone just there. Okay, so you're going to tell the examiner. It's all about setting it out now. So at B, we're going to resolve, and I'll need to tell the examiner that positive is in a certain direction. Well, I'm going to give the direction of motion positive, so positive is downwards. So you need to start thinking about constructing your answers properly. So R is positive, so downwards. So therefore 2mg, your net forces equals ma. And I ought to get you to start writing the formulas out beforehand, because having marked this year for the exam board, they want to see specifically what formulas you're using. So net force equals ma. So I'm trying to improve the structure of your answers. Net forces is your 2mg is positive. Take away the tension equals mass, which is 2m times acceleration, which we do know is 4g/9. Okay, and it's times by that. Right, so clearly you can see that T will be equal to 2 mg's. Throw that over, it's going to be minus 8 mg/9. So make them all over 9. That will be 18/9. Take away 8 gives you 10 mg/9 newtons is the tension. Okay, so that's the tension in the system. Right, it then says show that mu is 2/3. For this one here, you're going to have to come to particle A now. So we're going to look at A, and we're going to resolve initially in the vertical sense. Okay, and I'm going to say up is positive. It's not moving, so I can choose whichever way you want is up. So R of the unknown, again, net forces equals ma. So the net forces there is R minus mg equals mass, which is m, times acceleration, which again is 4g/9. Okay, so R is equal to, throw that over, and you end up with basically mg plus 4mg/9 will give you a total of R being 9/9. Add that is 13 mg/9 newtons. Okay. Well, that was lucky, and I'm recording this as well. I'm miles away, sorry. There's one of my Freudian slips. Thank God someone's paying attention. Okay, it's miles away. Right, it's upwards. Yes, there's no acceleration. Okay, there is no acceleration. Deary me, to have that recorded. Anyway, R equals mg. Okay, so you've got, now the next one you're going to be used is F max is equal to mu r. Or we'll come back to that actually. Okay, I'm going to box that off because we're going to need to know F max. And to know that, you're going to be, again, at A, we're going to resolve in the direction of motion horizontally is to the right. So we're going to use net forces equals mass times acceleration. The net forces is your tension, take away F max. I'm going to just label that as F because I haven't done so. So take away your F is equal to mass times acceleration. It is m, and it is 4g over 9. So it is 4mg over 9. Now I know my tension from my previous workings, so that is your 10 mg over 9. I'm taking away F max, and it is F max because we are moving. 4 equals 4 mg over 9. Again, throw that over, throw that back, and you end up with F is equal to 4 take away from there gives you 6. So 6 mg over 9 will cancel down to F being 3 into that is 2 mg over 3. Okay, newtons. Now that's F max. So therefore, with this connection here, we know that F max is 2 mg over 3. We know it is equal to mu times r. Now r is mg as we worked off here. So we can divide top and bottom by mg, and you end up with what we need. Mu is equal to 2/3 as required. Okay. Right, that now brings us to the next bit, which is when B has fallen a distance of h, it hits the ground and does not rebound. Particle A is then a distance of 1/3 h from P. Find the speed of A as it reaches P. Okay, so this here has got to fall a distance h. So it's 6 marks. It says find the speed of A as it reaches P. So I'm going to go down here, and I've got to work out first of all my diagram here. So this is part B. I'm going to look at B. Okay, so look at B, and I'm going to use SUVAT. Okay, so SUVAT, and I'm going to give the sense of direction is positive in the direction of motion. Okay, so I know, if you want a little diagram of what's going on, of what you're thinking about, is there is B, it is 2m. Okay, it has got acceleration in that direction of 4g over 9. So 4g over 9, because it's still connected, 4g over 9. It has got a distance of h to fall to get to there. Okay, so h to fall, and we are going to find the velocity just before it hits the ground. We know here that it was released from rest, so u is 0. So my SUVAT equations, I know in this sense of direction, positive, well, u is 0, v is what I need, so that's v. I've got my acceleration, and I check, yes, it is positive. It is 4g over 9, and it is I've got the velocity. The distance I want, or know, is h. So the equation I'm going to use is v squared equals u squared plus 2as. I've got v squared is equal to nothing squared plus 2as. So I'm going to double that, gives you 8g over 9h. So my velocity just before it hits the ground is the square root of 8gh over 9. I'm going to leave it as that, meters per second. Okay, so make sure you're setting it out like this with your sense of direction. That's very important. These are all correct to that sense. The equation you've chosen to use, sub it in, get your answer, get the units. Right, that means that we're going to look at this particle now, and we know it's travelled a distance of h along here, and now it is going to be, the there's no force from the tension, it's gone slack, so it is now just a free projectile moving, but it is moving with friction trying to slow it down. So there's going to be a new acceleration. So you need to work out the new acceleration. So at A, we need to work out the new ax, okay? So the new acceleration. Now to do that, I'm going to do a little sketch of what's going on. Okay, it is moving, it's got mass m, it is moving in this direction. Okay, I'm going to say accelerate in that direction, so therefore I'm expecting my answer to be a negative, because the only force opposing that is your friction max. It is friction max because you're still moving. Okay, so to work that out, I'm going to use Newton's second law, which says net forces equals mass times acceleration. So I've got my, if I'm saying it's positive in that direction, and I usually do it on the title, so I usually say there, direction of motion, it is moving in that direction. So I've got net forces is minus F max. Now F max was worked out to be 2 mg over 3. So it is 2 mg over 3 is equal to mass times acceleration. So clearly the acceleration in that direction is a negative 2g over 3 meters per second squared. Okay, so that is the new acceleration. Right, now we can use SUVAT. Okay, and it says in the question, it says when B is full and distance of h hits the ground and does not rebound, particle A is then a distance of a third h. So it's only now got a third h to travel. So we're going to use SUVAT. So at A, SUVAT. Okay, so we want to know what speed it hits P at. So we're going to say it is positive in that direction, and in that direction A is negative 2g over 3. So be careful with these signs. The velocity in that direction I want, because it's still got velocity, we assume, because that's what it's asking for. So V, the final velocity is V. Okay, U is what we left with. So whatever this smacked at the ground with is what it was projected with. So that is the U. It is root 8gh over 9. So root 8gh over 9. Okay, and the distance S, I believe, is a third h. Yes, it is third h. So h over 3. So we've got everything we need there. We're going to use the formula that we write down, v squared equals u squared plus 2as. V squared is equal to that squared gives you 8gh over 9 plus 2hs. Well, that's a minus a, so that's going to make a minus 4g over 3 multiplied by s, which is h over 3. Okay, so we end up with it hits P at V. We're going to work this out, gives you 4g 9 over that, take it away, gives you 4gh over 9 square rooted, which will give you 2/3 root gh meters per second is what it hits at. Okay, right. Coming back onto this question here, the last part of it says state how you have used the information that the string is light. If you're asking for two things, the string is inextensible, means that the tension felt here is the tension felt there, the acceleration felt there is the acceleration felt there. If it's a light string, it has got no mass, and therefore if it had mass, that would obviously increase the acceleration down here. The light string's got no mass, and therefore it doesn't affect the acceleration. The mass of that won't affect the acceleration. Okay, is the one marker. Okay, because sometimes those can be quite awkward. Okay, so that's part C. Being light, the mass of the string won't affect the acceleration's magnitude, size in other words. Okay.